guys, welcome back. So now we're going to learn new things, a new chapter, which is your chapter 7. So we're going to study about acids and bases. Okay, so this one will be your first video, which our focus is to understand about the different theories about the definitions of acids and base. And then secondly, we're going to learn about conjugate acid and conjugate base. Thirdly, we're going to identify what is strong acid and strong base versus what is weak acid and weak base. And then from there, we're going to learn on how to calculate the pH value for any acids or bases. And you're also going to learn about pOH, pKW. Okay, so KW stands for AUTOIONISATION constant for water. And from there, we're going to learn about acid dissociation constant as well as base dissociation constant, which you're going to learn to rank between a weak acid and it's become a stronger acid. Okay, so we have three different theories which define acid and bases. Okay, so we have Arrhenius, Bronsted-Lowry, as well as Lewis. Okay, so these three different scientists have three different definitions for both acid and base. So we're going to look one by one. Okay, the first one, Arrhenius. Okay, so Arrhenius states that an acid must have H in its formula, which it will dissociate in water to produce H plus ion. Whereas for your bases, according to Arrhenius, it must have OH in its formula, which will dissociate in water to produce OH negative ion. Okay, examples of Arrhenius acid are just like HCl, HBr. Okay, whereas for bases, according to Arrhenius, is like NaOH. It must have this OH which will dissociate in water. Dissociates, in other words, we call it as ionize. Okay, NaOH and then KOH, MgOH2 and so on. Alright, but according to the Bronsted-Lowry, okay, so this one is in the terms of proton. If it's an acid, it can donate a proton. If it's a base, it's going to accept a proton. So your proton is actually H plus. Okay, so H plus. Okay, this one is either H or OH. Okay, according to the Bronsted-Lowry, okay, if it's a weak acid or weak base, it can have its conjugate partner. So if it's a weak acid, it's going to dissociate and forming conjugate base. Whereas if it's a weak base, it will dissociate in water, forming conjugate acid. So I'm going to elaborate further about this conjugate partner later on. Okay. Whereas according to Lewis, okay, so Lewis is all about accepting or losing lone pair of electron. Okay, so if it's an acid, according to Lewis, it must have the ability to accept a pair of electrons. Okay, so this one must be related to the compound which lack electron. For example, if we have a compound with a central atoms that has incomplete octet, so you only have maybe 6 electrons around it. So in order to achieve an octet arrangement, it must accept another lone pair of electron from another compound, from another molecules, or from another atom. So that is your Lewis acid. But okay, for example, okay, but if it's a Lewis base, it means it can donate a pair of electrons. That means it have extra pair of electrons, lone pair of electrons. For example, if you have ammonia, okay, so ammonia, NH3, and you know, if you draw the Lewis structure, there will be a pair of electron on the nitrogen atom. So that means this nitrogen on the ammonia has extra pair of electron which can be donated to a Lewis acid, and they can form covalent bond between each other. So in this case, our ammonia is our Lewis basis. And if I have BF3, okay, so this compound has incomplete octet because boron only have 6 electrons around it. Okay, so that means this one can be my Lewis acid. So NH3 can donate that pair of electron on the nitrogen to form a dative covalent bond with the boron in the BF3, resulting in ammonia becomes a Lewis base and BF3 become a Lewis acid. So Lewis is all about lone pair of electron. Okay, so you can check on your lecture note about the list of compounds that fit the definition for Arrhenius, Bronsted-Lowry, and Lewis for both acid and bases. So in this video, I will just focusing on the correct terms or the specific terms which can differentiate between these three different theories. Okay, so let's try to write down an acid or base dissociation equation according to Arrhenius theory first. Okay, so if it's according to Arrhenius theory, your acid going to produce H plus, whereas your base going to produce OH minus ion. Okay, so water act as amphoteric properties, which if it's reacting with the acid, this water will become your base, whereas if it is reacting with a base, your water will become your acid. So water has amphoteric properties. Okay, what is amphoteric? Amphoteric means it can behave both as an acid as well as a base. Okay, so HCl here is your acid. When it ionizes in water, it will form, okay, H3O plus, okay, plus Cl minus, so equals and equals. Okay, HCl plus water in the liquid form, H3O plus Cn minus. Okay, alright, so if it's a base, it will become Na plus, okay, plus OH minus. Okay, so if it is a base, you are not going to show this H2O. Okay, if it's a strong base, you will not show the H2O in the equation. You just simply NaOH breaking down to form Na plus and OH minus. Same goes on with this one. Okay, so the complete dissociation. Later on, I will explain you to further what is complete dissociation and partially dissociation. Okay, so Ca, it will form Ca2 plus aqueous plus 2OH minus aqueous. Okay, for your acid, you can also write HCl, okay, undergo dissociation without the presence of water, H plus plus Cn minus. If it's in the water, then instead of H plus, it will form H3O plus. Okay, so H plus or H3O plus are properties of acid. Okay, so now let's look for Bronsted-Lowry. Okay, so Bronsted-Lowry, you can see two different arrow is being used here. So one is reversible arrow, another one is just as one direct double-headed arrow. Okay, so what is the difference between these two? Okay, so you're going to use this double-headed arrow for strong acid or base. Reversible arrow are for weak acid or base. Okay, so it's going to relate with 100% dissociation. Okay, this one partially dissociation. Okay, sometimes we also call ionization or dissociation. Okay, so HCl in water, it will dissociate completely because HCl is your strong acid to form H3O plus aqueous plus Cl minus aqueous. Okay, whereas for your HF is a weak acid. So that's why we have that reversible arrow, because your HF only partially dissociates in water. So weak acid, strong acid. Okay, so it will form H3O plus as well, plus F minus aqueous. Okay, so according to the Bronsted-Lowry, if it's a weak acid, that means it's going to dissociate in water, forming conjugate base. Okay, so your F minus is your conjugate base. Okay, this one is your conjugate acid. Why does it a conjugate acid? So conjugate acid is formed when a weak base accepts a proton. So form a conjugate acid. Means it has that H plus, and that H plus can be donated to another base. Okay. Whereas a conjugate base is the result of weak acid donate H plus, so it form a conjugate base. So this conjugate base F negative can accept another H plus to form conjugate acid or weak acid. So conjugate pairs only present for weak acid and weak base. Alright, so this one, NaOH will dissociate in water. Since NaOH is a strong base, so we don't need this water. You can just simply dissociate completely to form Na plus aqueous plus OH negative aqueous. Okay, so for strong acid and strong base, we don't have any conjugate acid or conjugate base. It will strongly dissociate to form its two different ion. Okay, NH3 is your weak base, partially dissociate in water, forming NH4 plus, which is conjugate acid because it has that H plus plus OH negative aqueous, which is the conjugate base. Okay, so we're going to look at these three different equations to understand more about conjugate acid and conjugate base, which will be the product from dissociation of both weak acid and weak base. Okay, so conjugate acid means it has H plus. This one, conjugate base, it has lost H plus. Okay, so no H plus. Alright, so if you look at it, okay, so H2CO3 from HCO3 minus, it means it has extra H, means H plus present. So this is your conjugate acid. So it's a result of weak base dissociate and forming conjugate acid. Okay, so this one has no H plus. That means it's your conjugate base. So this one definitely a weak acid which lost its H plus and forming a conjugate base. Alright, so let's look at the second example. So H2PO4 negative, it becomes HPO4 2 negative. That means in the process it lost 1 H plus. So this one is your weak acid and dissociates to form a conjugate base. Okay, whereas your NH3 is your weak base. Okay, so it dissociates, forming a conjugate acid. Why is a conjugate acid? Because from NH3 it accepts that H plus. So now your NH4 plus has H plus. So automatically it becomes a conjugate acid. So you just need to remember a base will dissociate, a base will accept H plus and becoming a conjugate acid. If it's an acid, so it will lose that H plus and forming a conjugate base. Okay, so let's look at the third example. So we have this HClO which lose its H plus and forming ClO negative. So this one is your conjugate base from your weak acid HClO. Okay, whereas this one is your weak base. That's why it forms a conjugate acid with extra H plus here. So conjugate acid and weak base. Okay? Alright, so let's look for Lewis theory. Okay, so Lewis theory is just you need to determine based on the given Lewis structure. If it is lack of lone pair of electron, that means it can accept another pair of electrons, so it will become a Lewis acid. Okay, but if it has extra pair of electron that can be donated, so that one is your Lewis base. Okay, so examples of Lewis acids are cations like Na+, H+, alright, K+, and so on. Okay, so molecule with central atom that can have an incomplete octet. So central atom that can have incomplete octets is just for elements of beryllium, boron, and aluminium, which you simply just say Birbal. Okay, so Birbal elements can have incomplete octet, so that means it will become a Lewis acid. Okay, thirdly, molecules that have polar multiple bond. Okay, so later on in your semester 2, you will learn about organic compound. So you will come across with organic compound with multiple bond. Okay, so some multiple bond are polar, but some multiple bond are non-polar. Okay, so as a recap of your revision for your chapter 4 about polarity. So if there is different electronegativity between two different elements, so it will become a polar bond. Okay, so polar multiple bond are example of C double bond O. Okay, so this one is a polar bond. Okay, another example. So this one is a polar bond too. Okay, so delta negative, delta positive. Okay, so polar multiple bond exists in aldehyde, okay, ketone, carboxylic acid. Okay, alright. So, and then we have the non-polar multiple bond, which is for, so these two are polar because it have that C double bond O. Okay, and another example, if we have C double bond N, okay, whereas if it's a non-polar, it means two different atoms are, two similar atoms are bonded together, which is, for example, in your alkene. Okay, so this is non-polar because same electronegativity between these two, so no difference mean non-polar. And you can also have for your C triple bond C, which is your alkyne. So these two are non-polar. Okay, so polar exists in C double bond O. Okay, first. Secondly, C triple bond N. So these are polar multiple bond. Okay, thirdly, any central atom that can have an expanded octet means it can accept more pair of electron. Okay, the maximum is 12. Okay, around the central atom. So this one applies to central atom which is located above period 3. Above period 3 means period 4, period 5, and so on. That means it already have 3D subshell. So complete, it already have completely filled 3D subshell. Okay, so what is about Lewis bases? So Lewis bases, for example, any. Okay, so for Lewis bases, examples are any anions. Okay, so Cn minus, OH negative, Br minus, okay, I minus, and so on. Okay, molecules with lone pair of electrons on the central atom. For example, I have NH3, so I have pair of electron. Okay, so example, another example, Xe, if you draw F, okay, so the Lewis structure is like this, so 3 pairs of electron, that means this one can be xenon XeF2 can be a Lewis basis too. Okay, and then thirdly, molecules with non-polar multiple bond, which is in your alkene as well as in your alkyne or benzene ring, benzene compound. Okay, all right. So let's now learn about the difference between strong and weak for both acid and bases. Okay, so if it's an acid, okay, if it's strong, that means it will dissociate completely in water. Okay, in other words, 100% ionization. So there is no acid dissociation constant. So acid Ka is for your acid dissociation constant. Okay, this one is exactly the same like in your Kc and Kp, but now it's focusing on acid and bases. Okay, so let's now learn on how to write down ionization equation for strong acid. Okay, this one I have my nitric acid equals, so it will dissociate completely in water or ionize completely in water. So single double-headed arrow forming H3O plus NO3 minus. Okay, so secondly, my sulfuric acid. So 2H in front of the sulfuric acid, that means it will dissociate to release 2H3O plus. So it needs 2 water molecules to form 2H3O plus equals plus SO4 2 negative equals. So this one is a strong acid. So strong acid, 100% dissociation. Okay, so you have this one double-headed arrow. Okay, so if originally I have 0.5 molar sulfuric acid, that means it will dissociate completely to form 0.5 molar sulfate ion, and this one is 2, so 2 times 0.5 molar. Never mind, we're going to learn more about this later on when we are going to calculate pH value. Okay, so weak acid, it dissociates or ionizes partially in water. So partially, in this case, it will just be about less than 10 to 15%. Okay, so you're going to use reversible arrow to indicate the ionization process, which is only partially. Okay, so this one, it will have that acid dissociation constant Ka. Okay, so you're going to learn how to write down your Ka in your second video. Okay, so this is my carboxylic acid. So organic acid are weak acid. Okay, so HCOOH equals, reacting with water, liquid, it will partially dissociate, forming H3O plus equals plus COO minus equals. Okay, HCOO minus. Okay, secondly, HCN equals plus H2O, liquid partially dissociates in water, so that's why we use reversible arrow, releasing H3O plus equals plus Cn minus equals. Okay, so that is your weak acid versus your strong acid. Alright, so now let's look for base. So again, if it's a strong base, it will ionize completely in water, so 100% dissociation or ionization. Okay, so no base dissociation constant. If it's acid, Ka, so for base, it's Kb, base dissociation constant. Okay, so NaOH, complete ionization. So one double-headed arrow. So for strong base, we're not going to add water in the ionization equation. Okay, just breaking down the bases into its 2 different ion. So later on, you will learn that if we have 1.0 molar NaOH, that means at the end, we're going to have 1 molar Na plus and 1 molar OH negative. So after complete ionization, this has be turns to 0. Okay, so secondly, MgOH2, okay, equals, it's going to form Mg2 plus equals and 2OH negative equals. Okay, so if it's a weak base, it will only dissociate partially in water. So this one, again, you need to use a reversible arrow to indicate the partially dissociation process. Okay, so mostly organic base are weak base. Okay, ammonia is a weak base, so if it's a weak base, you need water in the ionization equation to form OH negative plus NH4 plus. Okay, so this one we have that. Same goes on with the weak acid. If it's ionizations in water, it will have conjugate acid and conjugate base according to the Bronsted-Lowry. Okay, so CH3NH2 equals plus water liquid. It will release OH negative equals plus, okay, so this H2O is made up of H and OH. So this one breaking down as OH negative. So this H will goes to the weak base. Okay, so that's why you have CH3 and H3 plus. Alright, okay, move on. So acid dissociation constant, exactly like your Kc and Kp expression, we're going to remove any pure solid or pure liquid from the expression because we assume the concentrations are constant. But for ionization equation, we don't have any solid, we only have water as a liquid. So therefore, every water that present in your ionization equation will be eliminated from the Ka or Kb expression. So Ka is for weak acid and Kb is for your weak base. Okay. For example, here I have my first example. Hydrogen fluoride ionized in water forming H3O plus and F negative. Okay, so your Ka is the product concentration over your reactant. So its expression is exactly the same like in your Kc and Kp. So Ka, I have H3O plus times with F negative and HF. So water is eliminated because water is a pure liquid and pure liquid has a constant concentration, so does not appear in any equilibrium constant expression. Okay, so secondly, I have this methanoic acid. Okay, another weak acid. So my Ka equals to H3O plus and then HCOO minus over HCOO H. Okay, alright, so let's look on how to write down the base dissociation constant Kb. So exactly the same like your Ka, any water present in your ionization equation will be completely removed from our expression. Okay, so your Kb is now OH minus, okay, time with NH4 plus over NH3. Okay, so this one, your Kb is equals to OH negative, okay, and then CH3 NH3 plus over CH3 NH2. Okay, if you have to identify which one is conjugate acid and conjugate base, okay, so let's use this example. This is your weak base, ammonia. So definitely your water will become your weak acid. Okay, so weak base forming NH4 plus, see this one become your conjugate acid. Okay, whereas your water will ionize and forming conjugate base. So acid, weak acid turning to conjugate base because it lost that H plus. So now its product conjugate base need that H plus. Okay, so weak base will turns to conjugate acid. So conjugate pair only present in dissociation or ionization of both weak acid and weak base. Okay, so value of Ka and Kb can be arranged in order of increasing or decreasing strength. Okay, even though Ka and Kb are used for weak acid and weak base, but somehow between those weak acids and weak base, we can still rank them in order of a stronger weak acid and a stronger weak base. Okay, so Ka value will shows you the percentage of ionization. So larger Ka or Kb value means that the weak acid or weak base has greater ionization in water. So that means greater ionization in water means more percentage of H plus, more percent of H3O plus or OH negative present in the water. Okay, so that means greater strength as a weak acid or weak base. Okay, so sometimes the Ka and Kb will be shown in the form of pKa and pKb. Now mind, you will learn about pKa and pKb after you learn about pH and pOH. Okay, so let's look at this. Okay, so pKa is actually negative log Ka. Okay, so that means increase Ka value means lower pKa. So it's just a simple calculation. Okay, if you want to convert between Ka and pKa, you just simply negative log Ka, you will get your pKa, and the relationships are inversely proportional. Okay, so the concentration of H3O plus is directly proportional to your Ka value. So concentration of H3O plus is directly proportional with Ka. Okay, and Ka is inversely proportional with your pKa. Okay, so this relationship is very useful for you to remember, and you need to memorize, because it will help you to rank the weak acid in order of increasing strength. Okay, depending on either you are given the Ka or pKa value. Okay, so whereas pKb is also works the same, but this one is for your base. So if it's pKa is negative log Ka, but pKb is negative log Kb, again, okay, the relationship is just simple. So concentration of OH minus is directly proportional with the Kb value, but your Kb value is inversely proportional with your pKb value. Okay, that means higher OH negative concentration means high Kb value but low pKb value. Okay, so let's look at this example. You're going to arrange the given acid, all of these are weak acid, in order of increasing acid strength. Okay, so look at the Ka value. Okay, try to remember. We said that H3O plus concentration is directly proportional with the Ka value but inversely proportional with the pKa. In this example, we only have Ka value. Okay, so the larger the Ka, that means higher H3O plus concentration. So we have here -5, -10, -4. So -4 is the smallest. Okay, so this is the highest. Okay, highest. Okay, and -10 is the smallest value, so lowest or weakest. So this one is the strongest. Okay, so it asks you to arrange in order of increasing acid strength. Okay, so increased Ka value mean increased H3O plus concentration means increased percentage of ionization. Okay, means increased strength as acid. Okay, still the smallest one, HCN, followed by ethanoic acid, which is ethanoic acid present in your vinegar. Okay, and lastly is your nitrous acid. So label increasing strength as weak acid. Okay, so we already look up for acid. Now let's look for your base. Okay, so again, increasing Kb value means increasing OH negative, means increasing strength as a weak base. Because of what? Because increasing percentage of ionization in water. Okay, so let's look at the given Kb value. Okay, so this one again, it asks you to arrange in ascending order. Okay, so let's look. The smallest Kb value is which have the highest power, highest negative power. So negative 10 is the smallest Kb. So C6H5 and H2 is the smallest. Okay, then negative 10 it means negative 8, which is NH2OH. After that, we have negative 6 versus negative 5. So negative 6 is smaller. N2H4, which is your hydrazine. And lastly is your ammonia. Okay, so label, increasing strength as a weak base. Okay, alright, so what is auto-ionization of water? Like I said to you, water has amphoteric properties. Okay, so water has amphoteric properties. That means it can exist as both acid and base. So exist as both acid and bases. Alright, so that means between two different water molecules, it can ionize each other. So one can be acid and another one can be base. But it only partially dissociates because water is a weak acid or it can be a weak base. Okay, so let's say this first one become your weak acid, We. So this is the short form for your weak acid. Wb is the short form for weak base. Okay, so when this H2O is a weak acid, so it will release H+. Okay, if it's according to your Bronsted-Lowry, it will release H+ and forming OH negative. So this is your conjugate base. So release H+. Okay, for your information, most of the ionization equation, neutralization reaction that happens, we refer to the Bronsted-Lowry definition. Mostly it fits with Bronsted-Lowry definition. Okay, so if one of the water becomes weak acid, another water will become the weak base, and it will accept that H+ and becoming H3O+, which is your conjugate acid. Okay, by accepting H+. Okay, so your auto-ionization water, if we writing down the KW expression is exactly the same like your Ka and Kb, but this one is focusing on auto-ionization of water. So it does not have water in the expression because water is a pure liquid, and pure liquid does not appear in the K expression because it have a constant concentration. So your KW is just simply H3O+, okay, and OH negative. Okay, so KW is a constant value, which if it's at the room temperature 25 degrees Celsius, your KW is 1.0 times 10 minus 14. So KW expression is this. KW value is constant and changing according to temperature. Okay, so normally if you are required to use the KW, you will be given in the question what is the KW value at that temperature. Okay, so if it's a neutral, okay, so actually from this KW value, which is KW equals to H3O+ versus times with concentration of OH minus, actually from here we can classify, we can calculate either a solution is acidic or neutral or basic. Okay, because from the KW we can see that the relationship between H3O plus and concentration of H negative is inversely proportional to each other. If the value is the same, so how to calculate the H3O plus concentration is H3O plus concentration equals to Kw divided by OH negative, or if you want to calculate OH negative concentration, is simply Kw over concentration of H3O plus. Okay, and from here we can say H3O plus concentration is inversely proportional with OH negative. Only when it's a neutron, it will have H3O plus equivalent to OH minus concentration. Okay, if it's acidic, that means we have H3O plus properties. So for acidic, it will have more H3O plus. If it's a basic, it should have OH minus. So the concentration of H2O plus will be lesser than the concentration of OH minus. Okay, so this is it. Okay, so again, how to calculate your H3O plus and OH minus concentration? By using your Kw equals to concentration H3O plus multiplied by concentration of OH minus, and if it's at 25 degrees Celsius, your Kw is equals to 1.0 times 10 to the power of negative 14. Okay, so no unit. Okay, so if you want to calculate concentration of H3O plus, it's just simply Kw over OH minus concentration, or if you are calculating OH minus concentration, it's just simply Kw divided by H3O plus concentration. So most cases, they will give you one of the concentration. Okay, so if it's acidic solution, acidic means it has H plus or H3O plus. So that means if concentration of H3O plus is greater than OH negative, so it's acidic. If it's a basic, it must have OH negative properties. So that means H3O plus concentration must be smaller than your OH negative. But if it's neutral, that means H3O plus and OH minus concentrations are equivalent. Okay, so let's revise. If you still remember back in your high school, pH of acidic solution is less than 7. For basic, pH is greater than 7, and neutral solution is pH equals to 7. Alright, okay, so let's look at this and let's figure out either the given solution is neutral, acidic, or basic. Okay, so HCl in the pure water, obtain a solution with H3O plus equals to 3.0 times 10 minus 4. Okay, so your autoionization of water at 25 degrees C is 1.0 times 10 minus 14. Okay, so calculate OH negative. So first, rewrite Kw, which is H3O plus OH negative. Okay, so you want to find OH negative. That means just simply Kw divided by H3O plus, where your Kw is 1.0 times 10 minus 14. Divide by H3O plus concentration, which is given in the question, which is 3.0 times 10 minus 4. Okay, so you will get your OH negative concentration to be 3.33 times 10 minus 11 molar. So must make sure you have the unit because it's concentration. Okay, so if you compare, okay, so your H3O plus is equivalent to 3.0 times 10 minus 4 molar. Your OH negative is 3.33 times 10 minus 11 molar. So negative 11 is smaller than negative 4. So H3O plus concentration is larger than OH negative. Therefore, this HCl is an acidic solution. Okay, so you have to compare between H3O plus and OH negative concentration to figure out either the solution is neutral, acidic, or basic. Okay guys, so now let's learn on about how to calculate pH and POH for strong acid and strong bases. Okay, why do I say so? Because for weak acid and for weak bases, it will involve a long calculation. So I don't want to focus on that for this video. So in this video, we will just learn on how to calculate pH and pOH for strong acid and strong bases. Okay. Okay, so as a recap, strong acid and strong bases dissociates completely in aqueous solution. So for example, here I have HCl, which ionized in water, forming H3O plus and Cl minus. Okay, if I have 0.020 molar of HCl, so it's completely ionization in water. That means the original concentration of H3O plus and Cl minus is 0. But after ionization, I will lose all the concentration of HCl because it complete ionization. That means it will become 0. So no more HCl present in the solution. But now we have H3O plus and Cl minus, which if it's 0.020 molar HCl, that means I'm going to produce the same amount, 0.020 molar of H3O plus and 0.020 molar of Cl minus. So final. Okay, so this one has 1 mole, so that means 0.020. If it's 2 moles, then you have to multiply with according to the stoichiometry coefficient. So now, how to calculate the pH of the HCl solution? So your formula for pH is negative log H3O plus. So the H3O plus from the ice table here, simple ice table, is 0.020 molar. Okay, so just substitute with the value and you calculate, press your calculator, you will get your pH to be 1.70. Okay, so pH, you don't have to write down up to 3 decimal places, just leave it to 2 decimal places at the maximum. Okay, alright. So pH scale. Okay, so relationship between pH and pOH. So if it's a pH is negative log H3O plus, if it's a pOH is negative log OH minus. Okay, if you are given a pH and how you're going to calculate the concentration of H3O plus, it's just simply 10 to the power of negative pH, or if it's on the calculator is anti-log and insert the negative pH value. Alright. So your pH and pOH is related with each other by pH plus pOH is actually equals to pKW. And what is pKW? Your KW at 25 degrees C is 1.0 times 10 minus 14. So your pKW is negative log KW, which is negative log 1.0 times 10 minus 14, which your pKW should be equals to 14. Okay, so your pH plus pOH is equals to 14. Alright, and the relationship concentration of H3O plus is inversely proportional with OH negative concentration. Okay, so and in the terms of pH and pOH, so increase H3O plus concentration, lower pH value. Same goes on, increase OH negative concentration, lower pOH value. Okay, so let's learn how to calculate a pH of the strong acid. So you were given 0.015 molar of HCl. So first write down the equation, ionization equation. So HCl equals ionized completely in water because it's a strong acid. So one double-headed arrow. Okay, it's become H3O plus equals plus Cl negative equals. So original concentration of HCl molar is 0.015. That means this one is 0 and 0. Final concentration, HCl completely ionized, so 10 becomes 0. Whereas we have 0.05 molar of H3O plus and 0.015 molar of Cl negative. Okay, so pH is negative log concentration of H3O plus, and according to the ionization table just now, we have 0.015 molar of H3O plus. And if you press your calculator, okay, you will get the pH to be 1.82. Okay, so now you are supposed to calculate the concentrations of H3O plus, Cl minus, and OH minus. Okay, so from the ionization of HCl, that means it's a strong acid, it completely ionized in water, releasing H3O plus and Cl minus. So initial concentration of HCl is equivalent to the final concentration of H3O plus and Cl minus. So just simply writing it down again, H3O plus concentration is 0.015 molar, whereas your Cl minus concentration is 0.015 molar as well. So how to calculate the concentration of OH minus? You have to relate with the Kw. So Kw equals to H3O plus times with the OH minus concentration. So OH minus concentration is Kw over H3O plus. Okay, so your Kw, okay, provided this reaction happens at room temperature. Okay, so Kw is 1.0 times 10 minus 14 over H3O plus concentration from the final concentration in the R's table, 0.015. Okay, so if you press your calculator, okay, now press your calculator, you will get the OH concentration to be 6.67 times 10 minus 13 molar. Okay. Okay, so now let's look at a different example, which is your barium hydroxide, which is a strong base. Okay, so a strong base, it will release OH minus. So every molecules of BaOH to your barium hydroxide, it will release 2 moles of OH. So initially I have 0.00035 molar of BaOH2. That means this one I have 0.0035 molar of Ba2 plus as well. But for OH negative, we have 2 moles. So 2 times with 0.00035, you will get it to be 7 times 10 minus 4 molar. Okay, so if you want to calculate the pH, you need to find out first the pOH. Why pOH? Because this is a base. Okay, so you have OH minus. That means you have to calculate pOH first, which is negative log OH negative concentration. So just simply substitute the concentration of OH, okay, which is 7 times 10 minus 4, and you will get your pOH to be 3.50. Okay, and pH plus pOH is equivalent to 14. That means your pH is 14 minus 3.15 equals to 10.85. Alternative method. Okay, so alternative method to find out what is the pH is by, okay, calculating H3O plus concentration first. Okay, then secondly calculate pH. That is another alternative method. So how to calculate H3O plus? Just simply relate your Kw. Okay, so Kw equals to H3O plus times with the OH negative. So your H3O plus is Kw over OH negative concentration. And this OH negative is equivalent to the given concentration. Okay, so that is the alternative method to find out what is your pH value for your barium hydroxide. Okay, to check your understanding, please try this quiz 1 and you will get the final answer to be its acidic solution. Okay, please make sure you try to solve this quiz 1 and submit to me in our Google Classroom. Thank you for watching and see you guys again in my next video. Bye bye.